I wear two hats. I also lead Paraxial. And at Paraxial, we're working with IELCAP as well as several other companies and individuals around the world to develop AIRS. You may have heard about AIRS before. Claudia's mentioned it. It's an automated imaging reading system. So what we want to do is basically develop something that will read the scan first and then determine, have the nodules significantly changed, or is there a new nodule? And if you could tell that, you could basically have the radiologist essentially save some time, not looking very carefully at the lungs. So, so essentially, we're looking at nodules 3 millimeters and greater. That's a pretty small target, and of course non-calcified. And we trained so far. This is a very preliminary report. This is hot off the press as of yesterday. But we've trained on thousands of I-ELCAP cases so far, and basically we're ready to show you now the very first results of the system fully running. And I just want to point out that you know, this is the first time I believe any system has been developed like this. So, but let's get into the details now. So we do have this is the full pipeline of the algorithms being used. And of course, there's a participant criteria that have to be passed and image quality controls, which are pretty standard across the field. But then we have algorithms that segment the lobes, the lungs and lobes. We have algorithms that do detection of nodules and segmentation of those nodules, as well as matching of those nodules. If you mix up two nodules, you could make a terrible mistake. So we recently measured the performance of that nodule matching capability, and we were achieving 99.5% accuracy on nodule matching. One thing you'll notice is that if you want to do this, you can afford 0 mistakes. So you have to get these algorithms up extremely high. The amount of work you have to do to just create the ground truth, to do that and to validate it is tremendous. And really the IELCAP team has done an amazing job on the clinical side to prepare data of this caliber to do this. I also want to point out that at the beginning, we have kind of a pass-fail situation going on. And you'll notice that we switch over to a confidence score. So every element of the algorithm says, how confident are you, is the algorithm in doing that specific task? So let's say we do lung lobe segmentation, and at time 1 and at time 2, we also do it, but we get a much smaller lung lobe volume. Well, our confidence really falls down when we see that kind of thing. So this will be a system not only that performs this task, but gives you lots of feedback as to why it came back with a low confidence score. So now this is, again, a very quick first analysis of the full system running. So we're starting off with 170 screening participants, which consists of 278 post-baseline CT scans. Remember, the radiologist reads the first scan, finds all the nodules, perhaps with AI support, but then from then on, this system takes over and says, has anything changed? So we've got about 253 scans, or exactly 253 scans that had no change going on as determined by IELCAP radiologists. Then we had 20 scans that had new nodules, and we had 18 scans, it should say, that had rapid growth of a nodule. There is overlap between the yellow and the red. We're still working that out, but obviously there's cases that have both. So what do you want to do? You want to be able to separate out the yellow blocks that are here and the red ones from the green ones. And you want to get as many of the green ones and say, you don't have to look at this carefully as possible. So what's the result? The end result was we got, first of all, 100% performance on both the new nodule cases as well as the rapidly growing cases. We had seen this in a smaller study we did on, and we saw it again here in the second study. Then on top of that, we got 44% of the cases that did not have anything going on recognized by the algorithm. And the ones in the dark green is about 140 cases or so. They fall into the low confidence category, where if you pushed us, we'd probably call it as there's not much going on here. But we would say if we're not extremely confident in the decision, we push it out. So this is our first result. Basically, 40% of all scans where we saw that we could advise that the radiologist does not have to spend a lot of time looking for lung nodules and measuring them and seeing if any new ones showed up. And we did that without making any mistakes on identifying the scans that had issues. So we're absolutely thrilled with this result. To our knowledge, this is the first fully working system that can automatically determine whether a set of CT lung nodules did not change, including new nodules as well. So we're very excited about it. Let me just point out that in order to get here, the things that are circled in green required the development of a full deep learning neural net algorithm, including training and testing and lots of ground truth, et cetera. So you can see there's 4 of those right here. And then, of course, more algorithms, traditional algorithms around it. So the preliminary data indicates that automated AI identification of non-changing lung cancer screening scans could potentially speed up radiological review in about 40% of cases. I think we're going to get higher, more like 50%, maybe higher than that. And further studies, of course, are needed to refine the system and better assess performance. And actually, I think future automated AI no change systems will need to also assess other organs and conditions. So instead of saying there's just no change happening in the lungs, be able to say it for the heart and for many other diseases that the radiologist has to evaluate. So again, we're super excited with these initial results, and you'll be hearing more and more about this at the I-ELCAP AIRS website, including we'll be releasing code on how we do this, and we hope to really engage with the community on how automated image reading systems should evolve and develop. Thank you.